Plants gather so much information from light. From the photoperiod, the amount of hours of light a plant receives in a day, it can determine what season it is. From the light intensity, or the light quantity it receives, it can determine whether it's in shade or whether it's in full sun. And from the light quality, the specific colors of light it receives, it can determine whether it's in man-made shade or whether it's in the canopy of a forest. There is so much research going on in the whole world of light quality. And that's why I'm here at NC State to interview Dr. Ricardo Hernandez to learn about the relationship between light quality and plant physiology.
The area under the curve is the total amount. If you integrate all the area under the curve, that's the total amount of micromoles.
It would be wide even if it was in narrow spectrum in a lot of it?
Yeah, if it's very narrow. So yeah, if it's very, very, very tall, then the area under the curve also becomes bigger. We can put eight different light qualities, temperature, air velocity, you know, and relative humidity. All out of
Out of a cooler?
Yeah.
So awesome.
You can see back there where we have those fans. So we create a laminar airflow through here. So when you grow plants indoors, if you don't have laminar airflow, you're losing efficiency on your plant growth. We have thermocouples to measure the temperature in the leaves and temperature in the substrate. And then we have, you know, of course, light quality treatments. Some of the different light quality here.
Good. Can I touch them?
Yeah, of course you can touch them.
Just feeling for that, you know, that normal thick leaves you get with the blue.
Yeah.
Oh, is this white LED right here?
Yeah, so this one, we have matched the spectrum, the percentages to the sun. Can you separate it between the percentages of each wavelength?
I don't know if I can. Wouldn't that be the peaks?
No, the percentage is the area under the curve under each of the wavelength integrates, right? But it seems very balanced. Of course, we always have a dip there, but the percentage is still the same. So this is matching the sun, including the far red. There's multiple ways to communicate with the plants. And among those ways, with the development of LEDs, where we can separate the different light colors, we found that this communication with the plants is more seamless and more straightforward by manipulating the light colors. Now we're in the process of learning the language, because we know some responses that are matched to specific light qualities, but there is so much more to understand and know to be able to speak the plant language through light.
How does your approach towards horticultural lighting, I guess, vary based on whether you're in the research world or commercial world?
So I think there is a synergistic approach between both. A lot of the research that we do in my lab is very applied to the commercial sector. So, and of course, we're always looking for academic freedom and academic development, you know, by publishing science. But I think in order to take this science and make a greater economic impact into society, there should be a seamless transition into the commercial sector. To give you an example, a few years ago, I did some research at the University of Arizona under my mentor, Cherry Kubota, and we were working at light quality and transplant production. And out of that research, I wanted to apply that research to the commercial field. Right, so we worked together with my business partner, John Jackson, and developed a startup, Grafted Growers, that was funded by the USDA for a small business grant. And we were able to use that science and then repackage it. And now we use it to produce transplants indoors.
Yep, from research to application. And that's one of the reasons I'm really excited to interview today, because we're going to talk about all this sort of new lighting research and how specific light colors affect plant growth. And then we're going to actually dig into how a grower can actually use this information practically.
Absolutely. UV light is one of those wavelengths that can steer the plant into doing unique things. All right? Most of the research done with UV light, and especially UVB. So we have UVC, which is under 280 nanometers. And
that's the one that's sort of dangerous to us.
Yes, and most of that gets screened by the atmosphere. So in order to have that here, you need a special valves. And then you have UVB, which is between 280 and 320. You know, there is, depending on the field and the scientist, just a little bit of wiggle room on those numbers. And then you have 320 to 400, which is UVA. Right, so most of the plant studies done under UVB have been done with UVB levels that are significantly higher than what is exposed on Earth. And that so if you do that, then you see an inhibition in growth, an inhibition in photosynthesis, you know, and sometimes damage to the photosynthesis apparatus. And but then if you dial that down and you use levels that are closer to what is outside or slightly enhanced, then you don't see that inhibition in growth. Instead, you see a morphological response where you make plants more compact and shorter. It also triggers some pigmentation. And to apply it more commercially, there is some research being done right now in other research groups where they're using UVB light to pre-treat the transplants so they get ready to be stressed, right? So they give them a treatment of UVB light so they harden up.
It's almost like a vaccine of like a little bit of UV light to hurt them a little bit so that they can tolerate.
So by the time they go to the field, not only they can tolerate the stress in the field, they have a better chance to make it. So that's one of the applications of UVB light and UVA light in general.
So why would a plant be shorter when exposed to UV light? What's I don't know. What's going through the plant's mind for why is it staying short?
Yes. So that's a good question. And so there is these pigments in the plant that are sometimes wavelength specific, but most of the time they can sense a range of the wavelengths. So one of those pigments, a cryptochrome, is able to absorb part of the UV spectrum, including the blue spectrum, and that triggers the responses of making the plant shorter. Some studies have shown that plants sometimes detect the amount of light by detecting the amount of blue light, right? So the plant saying, well, I'm on a high irradiance or high intensity flight by noting the high blue light,
so
right?
It's like it can determine whether it's in full sun or in shade based on the color. Not just how much light it's actually receiving, but based on the color.
Based on the color also. So in that sense, the plant, and this is a hypothesis now, the plant may be able to stay compact because it's probably sensing there is more, the cryptochrome is saying there's more blue light, hence potentially there's more light out there. And so that's one of the...
It's going to stay short.
Yes, stay short, and smaller leaf area, thicker leaves.
Blue light's pretty close to UV, and when I use blue light indoors, I often see the leaves getting really thick and sort of smaller leaves. So yeah, that's same sort of response.
Yeah, and we have seen that also under very low light levels, right? So where under low light levels, you expect for a plant to put their energy to expand the leaves, because we're under a low light level, let's expand leaf area to capture as much light as possible.
Yeah.
Right? But if you use high percentages of blue light to the total amount of light, the plant stays compact, right? So even though there is low light, it's still staying compact, right? So that's where the hypothesis comes, and some study has been done that, yeah, it's actually thinking there is more light because the amount of blue light to the total light, it's greater. And,
So like a grower growing indoors where they aren't going to be giving a whole bunch of light, they can almost trick the plant to grow the way they want by adjusting color to keep it that compact. Where if outside it was under the same amount of light intensity, it would grow tall because it thinks it's in low light.
It will stretch. Right?
It would stretch.
Yeah, it will change the morphology. You can still tie growth to the total amount of intensity of light, right? That's growth, amount of carbon put into the plant. But the morphology, right? So the plant stretching doesn't mean the plant is growing. It's just making the cells longer instead of actually dividing the cells, right?
Yeah, cool.
So another responses for blue light is also pigmentation. You know, a well-studied one is anthocyanin accumulation in the plant.
And that's the red color.
Yes, the red color. And then that goes also tied with UVB light and UV light. So we know when you have an anthocyanin on the top side of the leaf, it is now proven that serves like a sunscreen for the plant, right? So when it will prevent photoinhibition when you have a lot of light coming into the plant, right? So it develops a sunscreen layer. So, but it's also an antioxidant for humans, right? So if you're developing anthocyanin in edible crops, then it also be beneficial as a nutritional antioxidant value. But you can also develop anthocyanin as a sunscreen when you're trying to move transplants from the indoors to the outdoors.
Okay, so that's really interesting. So a grower then, you'd almost want your plant not to be red until the end. If it's acting as a sunscreen, it's almost reflecting some of the light away. You could keep your plant, I guess, you could make it so it doesn't produce that much anthocyanin until the very end so you can get the most amount of energy into the plant and then color it. Yeah,
it depends, right? It depends where you're growing. So if you're talking about a crop grown in the greenhouse, where most of the environment is optimized for the growth of the plant, yeah, you probably want a strategy where you want to increase the foliar mass and the fresh mass and the dry mass first. And if your end product is a red lettuce, then you can color it. And there is some research done at Michigan State and Purdue where they show you how to color the plant right now. But if your objective is then to produce a more resilient plant outdoors, so then maybe you want the coloration from the beginning, so it's protected against the damage of outdoor conditions.
Yeah, if you're growing it in full sun from the start. That makes sense. How can a grower practically incorporate blue light into their grow? And what lighting sources would they go for?
So it depends, again, what is the whole objective of the grower. You have the existing gas pressure lamps, such as high pressure sodium metal halides, available for supplemental lighting. Among those, probably the metal halide will have the more bluest spectrum. Now, with the new LEDs, now you can just provide only blue or high ratio of blue to accomplish the same objective.
Tried this one? Tasted it?
No.
The purple shamrock? It's like super lemony.
Oh, really?
Yeah.
It's interesting.
People are starting to grow it as an edible.
That one, that pot is for the corpse flower?
Wow. That's a huge bulb.
With some of my indoor grower friends, I've seen they use metal halide sort of in their vegetative state to keep the plants really compact, and then they move it to high pressure sodium to flower. I thought it was pretty interesting that you did some research recently that showed that even green light can keep plants sort of more compact, or getting into that sort of next phase after blue, we get into the green, yellow, red, or green, yellow, orange, how those lights can also keep plants compact.
So to clarify, so most of our research done indoors has shown that blue light makes, the higher percentage of blue light make the plants more compact. And in the crops that we worked, which is tomato transplant, cucumber transplants, and lettuce of certain cultivars, we've shown that the addition of blue light actually inhibits the compactness. It makes the plant less compact. Now, what you're referring to is a recent research that we carry out in the greenhouse, where we tested different LEDs light spectrum, and we found that, to our surprise, that the light quality they had a little bit of green coming out of a white LED actually created a more compact transplant, such as geranium and pansy, and than the one having no white diodes, means no green light, and having mostly blue and red. And so we're very excited about those results, and at this point we can't explain them, and but we would like to look more into that. And so again, it comes back, it's very crop specific, right? Because we're talking to the different crops with light, so generalizing now in terms of light recipe, it's probably less optimal for the growth.
Yeah, you keep finding all these sort of really niche responses to a specific species or even cultivar within that species, and yeah, it's pretty exciting that eventually we're going to move towards almost every variety having like a recipe list of light.
Or you can group the plants that respond similar to the lights, right? So instead of having one variety, maybe there is a group of 10 different commercial blow varieties that will respond pretty similar. Then you have a more versatile recipe, say, instead of having one per cultivar. Yeah. Or you can go to the side of the technology and being able to have a fixture that actually, with a push of a button, you can change the color depending not only on the cultivar, but the growth stage of the plant. Yeah.
Adjusting the light by growth stage to get exact morphology, and then guiding morphology to lead into increased photosynthesis.
Absolutely.
It's such an amazing little interaction.
A lot of the research done with green light commercially has shown that if you will put a leaf under the different wavelengths, you show that the green light, which is between 500 to 600, it's mainly, it's less absorbed than, for example, the blue and the red.
Yeah, the classic McCree curve.
Yes, absolutely, the classic McCree curve. Now, that measurement was taken on a single leaf, right? If you extrapolate that to the entire canopy, the top plants, which have the spectrum of the sun coming on them, they probably prefer that red and blue, right? Based on the McCree curve, they prefer those.
That's where the spikes of absorption are.
Yes, and then they also absorb some of the green light. Now, if you go down the canopy, all the blue and red light is gone. It's been absorbed already. So what is left? So you have the green light. So what are the plants? The plants that are lower, the leaves that are lower in the lower part of the canopy, that's the light they're using for photosynthesis, right? So then that curve may become flat, where every wavelength is just as important, right? For a high leaf area and high tall vine crop.
To get the penetration to the canopy.
Absolutely, to get the penetration. So green is equally as important as red and blue, especially in these crops that are high wire crops, right? Because that's why it's available for a lower canopy.
Is the green light used through the same sort of pathway with the same sort of like chlorophyll receptors?
So green light is less studied than the other wavelengths, but in terms of morphological responses, some of the research has shown that green light sometimes counteracts the blue light response. Right? So if we adding more blue to make it compact, and then you add a little bit of green, then you may counteract that compactness and not be compact anymore. Also, some research has shown that green light by itself also triggers shade avoidance responses. Right? So plants think they're under shade, they're under other plants, so they tend to stretch and tend to elongate.
It's almost like a far red response.
Exactly. And all the research has shown that green by itself creates shade avoidance responses. Far red by itself creates shade avoidance responses, but together it's even more additive.
Okay.
So supplementing green and far red, you can really stretch that plant.
That's a good one.
Yes, super.
So, what's that greenhouse up there?
This is a phytotron.
Oh, okay.
Phytotron.
So So there's like 18 chambers in here. These are called the C chambers, the smallest set of chambers. You know, this is the newest. This is it's not. So there, you know, we're replacing all the controllers because you have those and they hated them. And then, you know.
Wow.
With LEDs, yeah, yeah.
So is this your research?
This is not, but we're working. This is just testing the lights. We're working together with a couple of companies to see who can feed us the best LEDs. And we will.
Like efficiency?
Just something that has open source programming.
Okay.
We don't want anybody's controller. We want
Yeah.
to control. We want to tap it in here.
Okay.
And control
Drivers as well?
Yeah, we want to control 8 in 1 for us. You know, so they're trying to figure out a way to, you know, have 400 micromoles of each channel,
Yeah.
all the way from UVA to far red.
Does that mean UVA?
Including.
Okay, but not B or C. Just say. Okay.
Yeah. You know, that's a good shot right there.
That's pretty neat.
So then they have, so the C chambers were at the bottom, these are the B chambers. Right, so 1, 2, 3, 4, 5, 6, 12. There's like 12 in this side and 12 in the other side. So these are the A chambers, right? So the A chambers are.
Wow.
Right, so we have probably 12 of these ones, 12 of the B ones, more or less. You can go in the website to find the exact numbers, so how many chambers each, and then like 18 of the C ones.
All cool white fluorescence?
Those are cool white fluorescence T5s.
720 spike for the far red, or is that's just red 720?
No,
So
720 is far, right?
let's check out crop height. .530 at crop height. Wow.
What's red's role in photosynthesis?
So red is one of those wavelengths that is also well studied, and it's due to the fact that a lot of the first generation LEDs, you know, a long time ago were red. So growth-based, you know, we know that red has a high relative quantum efficiency, and then we know that it's absorbed very well by the photosynthesis systems. You know, it can increase the plant growth.
By high quantum efficiency, you mean for every photon going in, it's more likely to be converted into what's actually powering photosynthesis?
Well, to a fixed carbon.
To fixed
in the
carbon?
plant. Yes,
Okay.
yes. And that's what the microscope shows you, the relative quantum efficiency. But another also
Sorry, I
has
interrupted.
equally important, right, to this improvement in growth is also the relationship between the red light and the light that is just next to the red light, which is the far red light.
Mm-hmm.
Right? So that relationship controls the phytochrome, right, which is made of interconvertible proteins, right? So it changes the state, right, depending on how much of the red light versus how much of the far red light. And that change on the stage creates the active response or the inactive response.
Yep.
Right? And
I remember this back in my plant physiology class, and I remember also getting confused by this.
it is very confusing. But probably what the grower needs to know is that if the amount of far red light in the environment is greater than the red light, the response that is going to happen is more stretching of the plant. Versus more red light than far red, maybe the plant will not stretch, right? It will be inhibit the inhibition of the stretch. So that's how the grower can picture it.
Okay. What about red light and far red light's role in flowering? I've seen, is it with long day crops, they use far red?
Yeah. So far red light, again, you know, it goes all back to that night interruption. And it was shown that incandescent bulbs were very effective to interrupt the night and create a short day for the plants to flower. And so when you scan an incandescent bulb, you see that most of the light is red and far red. Right? So now using far red LEDs, there is a very interesting research based out of Michigan State where you can use far red light for certain LEDs for certain crops if you're more efficient at using this light to interrupt the night. Or you can even use other wavelengths for a specific crop to interrupt the night. But I will
interrupting-
probably refer you to them
Okay.
for that research. Yeah, since it's not my specialty. Yeah.
Sounds good.
Yeah. So we see that yeah, you have those shade avoidant responses on the amount of red versus far red. So you have more far red than red, you're going to cause stretching, and then the other way around. Now, so how do we use these? How do the growers can use this knowledge for their crops? So at the end of the day, you know, after at sunset, the amount of far red light, it's greater than the red light. So that's, you hear the phrase that plants grow at night.
Mm-hmm.
What really happens is plants stretch at night. So you go home, you look at your tomato plant, it's this big. The next day, whoop, just stretched overnight, right? So the reason for that is they're not growing at night, they're stretching at night. And the reason for that is because they get a signal having more far red in the environment, and then sunset. So they know more far red, now I have to stretch, right? So that's ecological, right? So you can use that knowledge by saying, okay, if we want to stretch my plant, again, species specific, but stretch my plant even more, maybe you can supplement the end of day, right? Or if you're in an indoor facility where typically you won't have far red light, maybe you can use that far red light to stretch the plant. Or you can eliminate the far red light to keep it compact, right? Another interesting fact is that the response to that end of day far red light requires very little light. So if you move
the intensity of
in the
it?
intensity. So some research by Cherry Kubota at University of Arizona and showed that little intensity for tomatoes and cucumbers is like in the minutes, right? So you need 10 micromoles for 3 minutes. And don't quote me on the numbers, but it's to give you a point how much, like, you need very little light to create a great response. So going back to the grower, you need very few diodes and very little energy to create a huge response.
I think I've been seeing them space one far red like a little bulb light for every 10 square feet. So they space it out a lot.
Because that phytochrome response gets saturated very quick. Now another application may be for people that are trying to stretch for your vegetable grafting. You know, you want more room in your hypocotyl to be able to make the cod and put them back together. So maybe at the end of the day, you can stretch that, right? But stretching without compromising the growth rate. You still have a very high growth rate in the plant. You still keep the same stem diameter, but you're stretching the plant. So the stem doesn't become thinner.
It doesn't.
It stays the same thickness and it stretches, right? So that's a way that the University of Cherry showed that that's possible. So that's another application.
I always thought when you were giving it far red light that it was almost like stretching like a, like it was
like a rubber band, right?
Yeah, where like it gets skinny when you stretch it up.
Yeah. So most of the study done in tomatoes and some cucurbits has shown that the stem stays pretty close to each other between stretch and non-stretch plant.
Wow.
Right? By adding the end of the far red light. We also know that the far red enhancing your optimal spectrum for growth with some far red in it also improves the overall growth of the plant.
Huh.
And then there's different hypotheses of why that happens. One of them is like, well, you're stretching the leaves, you capture more light. That's one hypothesis. Other hypothesis is, well, you have an Emerson effect, where you have two wavelengths that independently create this much growth, but together don't create twice as much, they grow even greater growth. Right? So there is different hypotheses of why that happens, but we know now that adding a little bit of far red to your regular spectrum will actually increase the growth of the plant.
Wow.
Yes.
I've sort of been seeing almost a push from people who say plants can be grown purely with narrow spectrum, and people that say no, plants should get full spectrum. I guess, how do you see the balance of the two, of whether plants should be given a full spectrum, should be given green, yellow, far red, or can they get by with just lights that do blue and red?
So let me talk as a scientist first.
Sure.
I think the most tunability and control that you have is the better, because then you can capitalize on the full potential of talking to plants through light. That can, as a grower, and a commercial grower, I'll probably find a versatile fixed spectrum that will allow me to save energy by buying this LED technology, but also saving the money on having a less tunable fixture, but with high efficiency, right? So as a commercial grower, I probably look into the recipe that makes the most sense to achieve my goal, right? And then invest my capital in that. As a scientist, and hopefully looking into the future, the most control I have would be the better to fully capitalize in this.
Being able to adjust each color and figure it out.
So maybe once the cost of lights and technology drops in the future, then we have this knowledge now where we can say, okay, now any grower can program these recipes, and the lights will just change, accordingly to have their optimal output, right? So that's where I stand.
That's pretty exciting. I think we teased about it a little bit before, but the difference between light quality in sole source versus supplemental. Supplemental being sort of the classic way lighting has been used in horticulture for a long time, and sole source being indoor grows.
Yes. So now we know in the field that there is a huge difference in plant responses, right? Initially, we were trying to use the knowledge done indoors and try to directly apply it to supplemental lighting in the greenhouse, and we found that some of the responses were not matching. So we realize now that there's two complete different animals, right? And the reason being is because when you grow a plant in this greenhouse, you already have a full spectrum. You have most of the colors already present. Now that spectrum changes a little bit throughout the season, the location, in the years, and then, but it's pretty consistent. Right? So now you're adding another spectrum, under that umbrella of the spectrum. Now that spectrum may contribute very little when you have, long days and extended, or that spectrum may contribute a lot when you're in the winter, in the fall, under northern altitude, places there. So that response is how much the supplemental spectrum is contributing compared to the total spectrum, and what is that you putting extra into that spectrum is generating unique responses, right? So the research on that, it's when you move it now back indoors, you only have what you're given it. You have total control. So you can actually isolate those responses more quickly and try to develop a strategy. Outdoors, you have to actually test it and see if it's consistent through the season, right? Oh, it worked great this fall. It's not working very well in the spring, right?
Yeah.
So
because everything is about ratios.
Everything is about ratios. Yeah, most of it is about ratios. And then, so it's very interesting. In my research program, we like to pick some from the indoor, try to apply to outdoors, but most of the stuff is almost kept parallel. Unique developments that we see in the supplemental that we don't see indoors, and vice versa. But here we have the greenhouses. It's a greenhouse 1, right?
Yeah.
So all of these those greenhouses are AC cooled.
These are?
Yeah, no pan and fan.
That's
right, cold air, man.
Spoiled.
So in the middle of
Spoiled, that's what that is.
what is that? 24 600 watts?
this is 1,000.
Those are thousands?
Yep.
There's so much light.
It's like saturated. You want to guess?
No. Guess the microball? I'm gonna guess.
With the sun, 2,000? 1,000?
25? I'm gonna guess 2,500.
Oh, sorry, 13. Remember, with these reflectors, there is more light on the edges than directly under it.
1195. Wow, it seems so much stronger.
How much? 1,000?
1891. All right, that's closer.
That's very high, man.
Yeah.
For this time of year, I don't think we have that outside right now.
I guess, yeah.
We can check outside.
Summer is usually 2,000 or so.
Yeah, we
right?
can check outside. That's a good.
All right.
Let me see the spectrum. Oh, pretty cool.
Is that yellow spike, probably from the HPS?
Yeah.
You can't see anything in here.
What research are you currently doing sort of in both fields, in sole source and in supplemental?
So right now we have a couple of projects in sole source. We're looking for a dynamic spectrum. That's how we call it, dynamic spectrum. So we're trying to match the right spectrum to the right plant stage. And then we're looking at that and the interaction with other environmental factors such as CO2 and temperature. And the whole goal is to increase the grams of production per kilowatt hour of energy in that sense.
Cool.
Right?
So you could direct the plant responses like how blue light opens the stomata and then affect the environment or change the environment to increase more CO2 and sort of use all of these sort of ways to push the plant to come together.
Yeah, you can steer the plant. You can talk to the plant with this specific language. Yeah.
That's pretty exciting.
Yes. Now we're working on that on several horticultural crops indoors. Outdoor, on the supplemental, we have a project right now working with plant growth regulators, the chemicals, and using lighting strategies to try to get pretty close to the compactness of the chemical, to try to reduce the amount of chemicals used in the greenhouse. And then we also have another project working on how to create more compact plants through the season in the greenhouse. And also, we're always interested in looking at the diurnal response of the plant in terms of photosynthesis, right? So how is it regulated depending on the plant species? At what times of the day you have the most active plant in terms of photosynthesis, and when the plant starts going to rest or sleep, right? So we can try to match the supplemental lighting strategy to the plant rhythm, right?
Wow. So almost like spectrum mapped to the circadian rhythm of the plant.
Of the plant, yeah.
That's
so
pretty
those
cool.
are some of the projects that we're working in the lab.
That's pretty exciting. So where do you see the future of lighting research?
So again, I'm going to wear my scientist hat, and my commercial grower hat.
Sure.
So as a scientist, I'm more and more interested into the actual plant response, the ecophysiological response. Why are we achieving this? And then try to maybe start looking into the genetics at the same time. Currently, we're using conventional available cultivars, and we're trying to grow them indoors and boosting efficiency in the efficiency of growth, And then, so why don't we develop cultivars specific for indoors, right? That have a different genetic traits that are just for indoors. So I would like to develop a germplasm scan. First, find the best environmental indoor strategy to push the plant to the optimal whatever outcome. And then use that to scan exotic germplasm and see if we can even push that to find the right plant for the right light.
Find that one.
So that's
similar to sort of how the greenhouse industry did with tomatoes.
Exactly.
They started breeding tomatoes that could tolerate the high humidity and sort of the environment that you get in greenhouses, and then yields just started going up like crazy.
Yes. So I think we can do the first step there, and then maybe breeders can use that information, or use other genetic technologies to actually improve the crops that way.
And then we also talked about light recipes, and that could possibly be one of the future sort of areas where there's a lot of development of light recipes by crop stage.
Yes, so now let me wear my grower hat. As a grower hat, I don't want to be looking at the plant every day.
Yeah.
Like we do in our research.
Yeah.
I want to deploy my crop, deploy the recipe, and know that it's going to be the optimal we can get, right? So for the future, I think the science and the technology in terms of developers of light have to be in close communication to deliver a solution to the grower, and said, okay, based on this science, we're going to build it into this light, and we want to build this minimal viable product that will give the growers the tunability that they need. Not full tunability, only what they need to accomplish their goal. And then say, okay, tomatoes, press 1. Flowers, press, let's say, geranium press 2, or this set of flowers, press 2. And then, okay, leafy greens, press 3, right? And then, or you want it for more fresh mass because you sell it by weight, press 4. Or you want the most nutritional content because you have a unique marketing strategy where you sell your crops as higher antioxidant content, then press 5. right? And then so as a grower, that would be what we need, right? And then as a scientist, I want to get more into what is the language that we try to achieve more closely communication with the plant through the spectrum, right? So how can we communicate with the plant?
This seems like almost the newest, I mean, a lot of the horticultural studies have been looking at how to talk to a plant through temperature, humidity, sort of fertilizer. This seems like the most cutting edge of horticulture research.
Yeah, and we were benefited by the development of the LEDs. Right now we have this capacity to go into very, very detailed and specific wavelengths that is allowing us to discover these other ways to communicate with the plant. Yeah.
What is the grower's advantage, or why would they want a tall plant, or why would they want a shorter plant?
Yeah, so to give you an example, if you're growing high-wire tomato in the greenhouse and you're having to lean and lower that indeterminate tomato so often because it's stretching very fast, so maybe you can include a light recipe that will reduce the internal length between those clusters, and then you don't have to lower and lean it out more. If you're growing cut flowers, maybe you need a longer stem. So maybe you can develop a light strategy where you have a longer stem so you can have a more, right, a better quality product.
Yeah.
If you're doing vegetable grafting, maybe initially you need a longer stem to do the graft, but after they're grafted, maybe you need to make them very compact because a compact transplant is a better transplant.
And easier to ship.
Yeah, easier to ship, more hardy, less chances for it to break. You know, so those are the ways you can manipulate the light to match the outcome. Maybe you only have one cultivar and maybe a microgreen, and this cultivar you can use multiple right recipes to generate multiple products. The purple microgreen, the green microgreen, the white microgreen, you know, the spicy one, all maybe the same cultivar, right? But then you have the light and push the cultivar flexibility or plasticity to do different things.
That's pretty neat. All right, thank you, Dr. Ricardo Hernandez. This has been super exciting to visit you here at NC State, and I've learned so much. Thanks.
Yeah, thank you very much, Tyler, for coming. Thank you.